All right, so homework for today was to write added index and remove it index. How did that go? Should have been fairly frustrating with bugs. right on that cusp of insanity. I did warn you though, right? I mean, you knew going in that the surgery that you were going to have to perform was going to be fairly sketch. So let's dive in. Let's write these two, and then we'll have effectively a fully functional linked list. And then we're going to look at our next two linear linked data structures. We're going to look at stacks and look at queues, which are built on top of linked lists. And what's actually interesting is a stack is only add front, remove front. It's a very simplified linked list. And a queue is remove front and add end. Another very simplified linked list. So we've really written the worst part initially. And then the, not that linked lists aren't viable tools for just storing collections of stuff. From an algorithm perspective, we're going to be looking at, we'll probably write something called Towers of Hanoi, which is a stack-based thing. And then we'll write, what's the algorithm called? The shunting yard algorithm, which is for calculating mathematical expressions, taking order of operation into consideration. That uses both stacks and queues to do those things. So you'll see that the use of these tools that, from our perspective right now, are actually fairly simplified linked lists. You know, our version of easy linked lists, right? Can actually allow us to accomplish some pretty complex things. All right, so let's go ahead and we'll write added index. We're doing this inside of our linked list. So we'll say void add at index. And this guy's going to take an int payload as a parameter. And we'll go ahead and write our placeholder for our int remove at index. So when we added index, we're going to pass in the payload we're adding, as well as where we're adding it to. Remove at index, we're just going to remove whatever the thing is at index and return the int that used to be there. All right, so I'll steal these two guys. We'll go to our implementation here. We'll throw them in right here. I'm just going to return -1 in there for right now, just so when we go to test added index, we can test it without this guy crashing on us. So I'll just say remove an index, just currently always returns a -1. All right, so added index. So we're going to go ahead and we're going to do a couple of logical easy things. So we'll say if index is equal to 0, that means we're adding to the front. So we'll say this add front payload. Else if index is equal to the count, maybe. This get count. And we'll go ahead and say this add end payload. Else we are adding somewhere in the middle. And you could have written your, depending on how flexible you wanted your linked list to be, you could have written these two if statements. You could have said, well, if it's less than or equal to 0, you know, if somebody were to call it and say, I want to add this to bucket -7, if you want that to work for your linked list and just say, okay, you want me to add it to the front, you can make that work. But I think being explicit makes more sense. I want this to be the new front. I want this guy to be the new end. That's what those two things effectively are saying. All right. Otherwise, we're putting it somewhere else in there. All right. So if this is the case, then we are the ones who are going to actually create our node. So we'll create a node pointer n is equal to a new node with our payload. So now we created our payload. Let's go back to our picture. To my added index. So here's n. We just created our new payload here. Let me disconnect. All right, so this is maybe what our linked list currently looks like. We just generated n, this guy right here. All right, so now we want him to be at bucket whatever index was. All right, so he's going to become the new guy at that index. So right now, this is, let's relabel these. This is 3. We want this guy to become the guy at bucket 2, I think is the example used last time. So we'll pretend like that's our example right now. So I've passed in 2 here for our index for this guy. So what I need to do is I need to run up to either the guy right before him or the guy right after him. Doesn't actually matter, right? If I get to either of those places, I can do some hookups. Okay. So if I go ahead and do this 2 times, I can go ahead and get kernode pointing at either this guy or this guy. I can pick which one I want. So if I have indexes 2, I want to do this. I is 0. Is 0 less than 2? Yes. Is 1 less than 2? Yes. Is 2 less than 2? So I can say index -1 if I want to get to here, or I can say index if I want to get to here. So we're going to take kernode. In this case, let's just get it to this guy right here. So we'll say node pointer kernode is equal to this head. Then we'll write a little for loop for int I is equal to 0. I is less than index -1, I plus plus. Kernode is equal to kernode get next node. So that will run kernode down the list to the position in our list immediately following where this new guy should be inserted. Make sense? So if index was 2, we start off at head. Is 0 less than 1? 2 minus 1 is what my code currently says. Index -1 right here. So is 0 less than 1? Yes, it is. So kernode equals kernode get next node. Is 1 less than 1? No, it's not. Boom, we're where we should be. Okay, so we position kernode at the correct place. Now we start doing our surgery. So we're going to set n's next node to point to the same place as kernode's next node points at. And set next node to kernode get next node. All right, so that does this guy right here. That makes n's next node point to the same place that kernode points to. Kernode's next node points to. All right, then we're going to set n's previous node is going to point to cur node. And set prev node is going to equal cur node itself. So that's this guy right here. So we have made n point to the correct places, right? So now we're going to go ahead and set cur node's next node point to n. Cur node set next node to n. So that did this guy right here. Then we're going to say n get next node set previous node to n. So n's next node, which points here, we want to set his previous node to there. N get next node set previous node to n. All right, have we inserted it at the right place now? Looks like it. One last thing we need to do, we did just add something to our list. We need to increment our count. This count plus plus. All right, so that should be add at index. So let me see what this dude currently looks like. All right, so I have a 4, 3, 2, 1, then a 14. So this is bucket 0, bucket 1, bucket 2. So let's add an 11 at bucket 2. LL add at index and 11 at position 2. So 0, 1, 2, here's our new value at position 2. And everything else still goes through. Let's add this guy at position 1 instead. Now our 11's at position 1. Let's add it at position 0, which should call add front. Let's add it at position, 0, 1, 2, 3. Actually, let's add it at position 4, which is not equal to count because count is currently 5. So it should be the new second to last guy. Yep, so there's our 11. This links to 14. And if we put in a 5, that's going to be the add end, which calls our old add end, which we had already tested. All right, questions about that one? So where's the complexity here? These 4 magical lines. Not a whole lot of code, but very specific code. Okay, when you perform that surgery and you insert that node, it needs to go in the right place. Go ahead. Well, right now my code's gonna, it just won't do anything, right? If I say, actually I have it inside of an else right now. So right now it's gonna fail right now because I'm gonna try to run it to, I'm not error checking for like a negative something or something bigger than that. So I could do an else if in here and say, else if index is less than 0 or index is greater than this count. This, I'll just say this, that get count, even though I do have access to it here. And then I can do something like C out illegal position. Something like that. And that would just catch it. Otherwise, you're going to be at the mercy of what does this for loop do based on what index you passed in? Which would then start giving us, I think what we would have seen last time is we don't get a segmentation fault in this compiler. So instead, it's just going to, we won't have output, which I think is pretty frustrating to write something and not have any output, but you're welcome to use a different C compiler, Eclipse or something like that. I just am using this to match what I am officially supporting in class, so I don't have to have you come into my office and saying I can't get Eclipse to compile or Visual Studio is not running my code or something like that. All right. That makes sense? So, I mean, if you didn't do this, that's fine for your homework. I'm basically looking for that dude right there. Run up to one of the two positions you got to be at and write your 4 magical lines to do the surgery. And that's kind of what's frustrating with linked lists, I think, is that in the end, the amount of code you write to implement stuff is not a whole lot. It's not many lines of code. It's just frustrating lines of code, especially if you didn't draw pictures. Hopefully all of you have begun drawing pictures, even though I've been saying that for 3 years, or I guess a year and a half now, right? Draw pictures. it will make your life easier. Okay. Any other questions on the added index? All right, so let's go ahead and let's write remove at index. So we'll say if index is equal to 0, we'll return this remove front. Else if index is equal to this get count -1, which would be the last legal bucket in our list, we will return this remove end. Else, if we want to play catch all like we did up here, I'll just throw the same if statement in here for the illegal position. So if you give me something that is, we can say greater than or equal to count. So we're gonna, because it's a 0-based index, so count would be not a legal position on it. Count -1 is the last legal position. So this says, hey, if you give me a negative number, or you give me a number that's too big, I'm just going to scream at you and not try to do anything special. Else, we are removing a value in the middle. All right, so we go back to our picture. This dude right here. And we're going to go ahead and we'll hook them back up. Debut. Did any of the rest of you, when you saw this, think this is like a little spaceman? He's floating away and these two guys are grabbing him, trying to keep him from flying out into space? Or is that just a me thing? A human pyramid? Yeah, like you mean from like not gymnastics, but cheerleading? I always had to be on the top. See, get the football team out there to. All right, so this is what our thing currently looks like. We need to, the guy we're going to remove is this dude right here. So he's at the index that we're going to remove. So I'll go ahead and reset those to where they're going to be. So if I want to remove index 2, what do I need to do? I need to run up to, now I can, frankly, I can make this work from this position, or this position, because I have a doubly linked list now. You know, the various levels of scary lines of code for the 4 lines that we're going to have to do for our surgery, but I can make it work from any of them. But we'll go ahead and let's run up to our actual position we're going to remove. So we'll say node pointer cur node is equal to this head. Point at the beginning. Orient I is equal to 0. I is less than index. I plus plus. So we're going to run up all the way to the guy we want to remove. Cur node is equal to cur node get next node. Make sense? So that started cur node off here at bucket 0. Is 0 less than 2? Yes, it is. So cur node equals cur node get next node. Is 1 less than 2? Yes, it is. So cur node equals cur node get next node. Is 2 less than 2? No, it's not. Boom, we're where we should be. So we're pointing at the guy that we ultimately want to disconnect. All right, now we want to remember the value that we're ultimately going to return. So in my little picture here, I called that temp. Int temp is equal to cur node get payload. Okay, so we'll remember that dude. And we can even right now, we can say return temp. So we don't forget to do it. All right. So but we need to put some more lines of code in here because remember, return makes a function immediately end. All right, but a good rule of thumb might be is if we just preserve the value that we ultimately want to return, we can go ahead and put that return statement in and then build our sandwich in between. I would say it's a fairly common mistake to preserve something you want to return and then forget to return it. And that's a bigger problem in a language like C or C++ because it won't yell at you. You know, Java will say, hey, you told me that you were going to spit out an int, but you didn't. So in Java, you can go back and say, oh, I forgot to return it. But in C++, it just, yeah, no problem. You don't want to return something, don't do it. Okay. So we'll build our sandwich in here. So now we ultimately want to disconnect this guy. But before we can do that, we need to say cur nodes, get previous node, set next node to cur node, get next node. That's a good one, right? So cur node, get previous node, set next node to cur node, get next node. Cur node, get previous node, set next node to cur node, get next node. Super ninja move. So that gets us cur node, get previous node, set his next node to whatever cur node's get next node is. Similarly, cur node, get next node, set previous node to cur node, get previous node. Cur node, get next node, set prev node to cur node, get prev node. Cur node, get next node, set previous node to cur node, get previous node. Then we could say cur node, set previous node to null, cur node, set next node to null. Cur node, set previous node to null, cur node, set next node to null, delete cur node. Get rid of the memory for that dude. So we'll disconnect this and then we'll go ahead and say, all right, you are marked for deletion. Give it back to the OS. We have previously preserved the value that we're going to return. And we'll go ahead and return it. And then if we want to reconsider the indexes in there, it's going to look like that now. All right, let's test this dude. Oh, we also need to remember before we return this count minus minus. Because we're the ones in here who did the disconnecting, we are the ones who are responsible for decreasing the count in our list now. Up here, it would have been handled for us with remove front or remove end, because we wrote it into remove front or remove end. It's a very sad day now. Okay. So let's go ahead and test this dude. So our list looks like this. So let's do a, let's see, 0, 1, 2, 3. Let's remove at 3. So that should get rid of this 1. Four, 3, 2, 14, 11. 1's gone. Let's remove at 1. So that should get rid of this 3. Yep. Let's remove at 0, 1, 2, 3, 4. Yep, that removed the 14. So you notice I'm testing the places right inside the beginning and the end. Those tend to be sometimes places where errors can occur in linked data structures. Sometimes you need to, depending on the data structure you're working with, sometimes you need, and the way you're going about it, sometimes you need to treat those as special cases. In our case here, we didn't have to, but it's a good thing to test, you know, the extremities, which our extremities are going to be easy, right? Because we already wrote those and tested those, as long as you make sure you call remove front or remove end. And then this guy will be that'll remove the other end. Got rid of the 11. Okay, so that should be remove at index. All right, questions on that one? So it should have been really this dude right here. That's our bulk of our logic here. The rest of it's just, am I removing the beginning or the end? If so, call the other functions that we've already written. Remembering to return what those other guys do. Another kind of common mistake we might do here. Remove an index will return an int. So if you've asked us to return the thing at the index or remove the thing at index 0, no problem. You just need to call upon remove front, which returns an int. So you then need to return whatever that guy returned. Don't forget to spit the answer out. Because if I don't do the return statement there, this will, in fact, remove it. But we won't get the answer flying out of here in case somebody wanted to use it. All right. So questions on that? So after this assignment, you should be pretty comfortable using pointers at this point, right? All right. So realistically, depending on whether this worked out for you the first pass or not, this assignment could have taken as little as, what did we do it in 35 minutes or so by saying it out loud and doing things. So let's say as little as 30 minutes or as much as 4 days, somewhere in between, because debugging the pointers can be very difficult. And the starting point for that is to literally go back to your picture and follow what you're saying to do step by step and see where did you leave some soldier behind. That's almost always the case, right? You pointed to some null. Actually, it's almost always the case that you asked nothingness to do something. That's what's almost always the case with pointers. And you can pretty much be guaranteed that's the case when you get a segmentation fault, which in here at this point, we're viewing as nothingness, but I don't know for sure if it gives us nothingness under other circumstances as well. But with linked data structures, it's almost always that you have asked nothingness to do something, which we know doesn't make sense, but that doesn't mean that's not what you told it to do. All right, so maybe the very last thing that our universal integer-based linked list needs to know how to do is maybe just get at index. Sometimes we want the value that lives at bucket 3, but we don't actually want to remove it. We just want it. Make sense? So we'll go ahead. We could almost think of this as the strings char at method, something like that, or getting the index of an array. So we'll say int get at index. This is going to be pretty similar to remove at index, well, except not removing it, which means we won't have to do all the weird hookup things. All right, but we can steal. Actually, we really only need to steal the error checking piece of this. We could write get front or get end. We could do that, but I think that might be sort of overkill, because typically if we're just getting a value from a collection, we're going to say, hey, this is the index I want you to give me, go get it for me. So we would give it a 0, or we would give it the count -1, that kind of stuff. All right. So if they gave us something that was illegal, we'll scream at them. Else, we want to zip up to the value that we want to get. So node pointer cur node is equal to head. And just say for int I is equal to 0, I is less than index, I plus plus, cur node is equal to cur node, get next node. So we'll zip it down the line and then return cur node, get payload. So that should get us the dude at the index. Okie dokie. And we can test that here real quick. So we'll go ahead and do a C out, LL, get at index. We'll test it on 0. And then we'll do another display just so you see that it did not change our list, but we just saw the implementation of it. And we clearly saw we didn't do the crazy stuff. So we know we didn't write it to display our list. Oh, what did I do? Same error as last time. I said, I'm going to write get an index. What did I forget to do? Yep, this dude. Didn't say you belong to this class when I was implementing it. All right, so bucket 0 is a 4. Notice I didn't change it. So then we have what? Bucket 0, 1, 2, 3, 4. So we'll have it give us a bucket 4 now, which should be a 14. So there's our 14. Then we'll have it, let's see, 0, 1, 2, give it bucket 2. And there's our 2. All right, so now we have the ability to go and look stuff up in our linked list. Okay. Next. We're going to implement a stack. Go back here for a second. So I'm going to add a new file. So this guy is going to be called stack.hpp. And this guy is going to be a class stack. I'm gonna have to look up the syntax here in a second, but I'm pretty sure it's that. So no longer am I just having a class directly inherit from objects. I'm actually saying I want a stack to actually be a linked list. It's an implementation of a linked list. Now I could write it again. So if we didn't already have our linked list, we could implement a stack as like a very simple linked list. No harm, no foul. In fact, you're going to be doing this when we get to our homework assignment. All right. But let me just quickly make sure I'm using the right syntax here. Looks like it might just be a single colon. I have to put public in front. It seems kind of stupid. Oh, it tells you which things you have access to. Oh, that's kind of interesting. Okay. Wonder what happens if I just leave it like that. Bet you this works. Syntax I'm seeing there is something that looks like that. But I'll be able to answer it here in a second. So I'm building a class called stack, and this guy's going to be built in terms of a linked list. And a stack is going to have, we have our I even need a private section. I won't in this case. Typically, instead of the head of the list, a stack has a top of the stack. Same thing, it points to the first element. All right, but a stack, go back to the notes here. Stack is a last in, first out. Linear linked data structure. So you can think of this like a stack of newspapers or a stack of magazines. You put something on top of the stack, the last thing you put on will be the first thing you take off. You add to the top, you remove from the top. All right, so 3 functions. For stacks, technically, 2 of these are required functions under the abstract data type called a stack. I really think 3 makes more sense, so we're going to teach it as 3. So we have push, pop, peek. Push pushes an element onto the top of the stack. Pop removes an element, removes and returns an element from the top of the stack. Peek returns the element from the top of the stack without removing it. That's the one that's not 100% required by the abstract data type, but I think it's pretty handy to be able to say, I want to look at what's at the top of the stack without actually changing the stack. Okay, so those are the 3 functions that we're going to write for our stack. So we're going to have public functions here. And for our starting point, we're going to keep our, we're going to stick to what we did before, where we're always returning an int. So we'll say int, because again, this is going to be a stack of integers, just like our linked list is currently a linked list of ints. Pretty quickly here, we're going to be moving to a linked list, or in this case, a stack of objects. All right, when we write Towers of Hanoi. All right, so we're going to say, peek void push, call it payload like we did before, int pop, int peek, So we'll go ahead and implement this inside of stack CPP. All right, so there's our functions. Push is going to take in our payload, and if we're always pushing to the front of the stack, we'll say this add front payload, because a stack is implemented in terms of, as we've written it here, a linked list. Therefore, a stack has an add front. So push means add to the front of the underlying linked data structure. Pop will return this remove front. Peek return this get in index 0. Add front, remove front, get it index 0. Now we do need to create a constructor for this dude. So we'll have a stack, creates an empty how do we want to write this? Should be able to just do that. Let's see if that works out. Oh, and these need to be these guys. I expect we're probably going to get a couple of errors. It's not accessible within this context. Okay, does that mean that here I do need to say the public thing? All right, super. I need to get at that parents class. Oh, that's interesting. Let's do the colon. All right, so we'll come back on Wednesday so I can get this working. In the meantime, just so I give you a good base start. If you want to look at Towers of Hanoi, this is what we're going to be implementing. You can like play it online here. This guy. So we're going to have 3 stacks. Each tower is a stack. And the idea is you get all these things over to the far right, but you can't put a larger disk on top of a smaller disk. That's illegal. So we're going to be implementing a text-based version of this guy using the stack that we're going to build, but we're not going to have a stack of ints. We're going to have a stack of disks, where each of our stacks is called the tower, so on and so forth. Okay, so if you want to familiarize yourself with this game, just do a search for Towers of Hanoi. We'll come back on Wednesday, finish up our stack implementation, and start our implementation in preparation of Towers of Hanoi. Questions, comments, concerns, bribes? I'll see everybody on Wednesday.